נכון ממוצעי פלישה, אני לא זוכר כמה זה האחוז, אני גם לא יודע מה הקו של המערה הזאת עכשיו. אבל תשמע, מי שלקח אותנו לשם, זה קיים גרעינים שלא לא מזיעים. זה של עידו. עידו בטח ידע להגיד לך בדיוק איפה זה, אני מאחר את זה. של עידו, אני חושב שלא, אבל להבין בוודאות כן.
נקודה. זה משם מתחיל. שם גם לא יודעת איך להסביר את זה.
לשתף לך את הדפייה? או שאני יכול?
מה שלא יודע. אבל הוא הולך ככה.
זה אומר שיש לך גישה צפייה על
לא
הדפייה.
צריך להסביר לפעולות, אבל קצת קשה להסביר. כי אם הוא היה קצת שמאלה, אז הוא כאילו היה בורח.
לא צריך להסביר למה, צריך להסביר מה קורה, לתאר,
לא, אני רוצה להבין למה, לא יודע, זה בסדר.
אני אגיד לך למה, בגלל שהאלמנט של C1 הולך, אז הוא לא שולט.
זה מה שרציתי להגיד. מה?
כן, זה נכון.
זה מה שרציתי, זה כאילו, זה מה שהתלמדתי.
Absolutely right. שתי מקומות.
זה זה
אני אמרתי לך, אני אחת בשיעור, אני זוכר נכון. וואי, זה חמוד.
וגם, לא יודע אם צריך להסביר, זה לא צריך להסביר. לא, את אומרת ששאלת אותי להסביר למה זה, אבל הופענו...
אתה יודע למה שאלת?
כי היא הסבירה.
הסברתי.
הסברת?
או, ראיתי.
Hi everybody, I'm sorry for being late. I'll start right from where we finished last time. where we were analyzing a 2D system, a linear 2D system. Right? And we saw that we can immediately know the properties of the fixed point at the origin by calculating the trace and the determinant. So minus 9 and 14, this is somewhere here. And our parabola marking the border between regular nodes and spirals passes above this point. So this is a regular, stable node. And then we could find its eigenvalues. And then we have lambda 1 equals minus 2, and lambda 2 is minus 7. And of course, this makes sense. So there is only decay into the origin in this system. And then I promised that I'll show how to find the eigenvectors. So I do this for each eigenvalue at a time. So I start from lambda 1 equals minus 2. And by definition, this should meet this condition, okay? And I'm looking for the vector that meets this condition when I know A and I know lambda 1. So I just, first of all, I will give names to the two components of the vector. They will be U1 and W1 because this is the first eigenvector. Actually, let's use S1 and R1 because we'll see U and maybe W later in this lesson. Okay, so now I write the equation explicitly. And here, this is actually a set of two equations, but I will only take one. I only need one equation, so I choose arbitrarily the first one, minus 4s1 plus 2r1 equals minus 2s1, and then I solve this. So I find that the two components of the eigenvector are equal. And now it doesn't matter, of course, what I choose, okay? So I choose V1 to be 1, 1. Okay? Doesn't matter what I choose. Any multiple of this will also obey this equation. And in fact, this eigenvector is an eigendirection. We don't care about the length of the vector, only about its direction. Okay, if you do the second equation, you can see that it leads you to the same condition on R1 and S1.
But in some situations, you have to use both rows. But this would only be
are
independent, where do you need to solve the system?
R1 and S1. No, we're not talking about the dependence of R1 and S1.
Okay.
Okay.
Never mind.
They're,
Yeah.
they're anyway, they're tied to each other. Okay. Now I do this for the second eigenvector, the second eigenvalue, lambda 2 equals -7. And now I will have V2 as S2 and R2. And then -4, 2, 3, -5. Okay. -4 S2 plus 2 R2 equals -7 S2. So 2 R2 equals -3 S2. And this is my eigenvector. Okay, you can keep solving this, but you can also see that this meets the condition. And now I have everything I need to know about the system. I have its eigenvalues, its stability, and its eigenvectors. And I can draw the phase portrait. Okay, so what I draw here will be a complete phase portrait for a two-dimensional system. I know that there is a stable, let's do this in a different color. I know that there is a stable fixed point at the origin. So I mark a filled circle. And I can already draw my eigenvectors. Okay, so this will be my first eigenvector. And I'll mark the scale. The second eigenvector is 2 and -3. I'll give them their names. And now I know, because these are eigenvectors, I know that on these directions, the system goes directly into the fixed point. Okay? On V1, there is a decay with a constant of -2. So what I do here is mark trajectories. These are, in fact, trajectories of the system. Sorry.
Can you remind us what is the reason the trajectory is
Going in. Because the eigenvalue for this eigenvector is negative. So we have a decay that is like e to the -2t. Okay, also on this direction, here there will be a faster decay because the eigenvalue is -7. Okay? So this means that when I am far away from the fixed point, the faster decay will be parallel to V2. So I can imagine two components looking something like this, and the net the net vector acting on this point will be in this direction. Okay? So these are the considerations I use in order to draw the trajectories that are not on the eigenvectors. Okay? Repeat this. Okay. In a direction, in a point that is far away from the fixed point. Okay, and okay, far away from the fixed point around here, there is fast decay along V2 because lambda 2 is -7. Okay, so a system that is located here, say this is its initial condition, feels feels a kind of force, okay, that is strong parallel to this direction and it's weaker parallel to that direction. Okay, so I can make this vector diagram, and adding these two vectors gives me this net vector.
The distance of V2 and V1 is the same, or does it matter?
Well, it matters a little. I'm saying that it's approximately the same, and it's far enough. Okay. So I'm going here in order to see the general case, and then I will be able to treat the vicinity of the eigenvectors. Okay. So the system feels this kind of force. Okay. If we would move from the xy coordinates to coordinates on the eigenvectors, then we will have a large derivative on this dimension and a small derivative on this dimension. Okay? It's hard to translate this to x dot and y dot, of course. But you can imagine that this point here feels a strong attraction on this direction and a small, weak attraction on this direction. And so the net vector acting on it is going there. Okay? And then from here, it will go here, and so on and so on. Okay? Every time it approaches the fixed point, the component of V2 is becoming smaller. It's decaying faster and faster, so it's becoming less dominant. Okay? And what we have here is a trajectory that is going fast along the V2 direction and more slowly along the V1 direction. So a system starting from here is immediately pulled very strongly to the origin along the V2 direction. Okay, this is a dominant pull because this eigenvalue is -7 compared to the -2. And only after this decay has been going on and it's taking the phase point close enough to the origin, then we see the decay along the V1 direction. Okay? And this is what the system will look like. The trajectories. And you can fill this with trajectories. The drawing here is quite rough. Okay, you're not expected to know exactly how to draw the trajectories, only to show the correct curvature. So when we are far away and we are dealing with big numbers, big multiples of our eigenvectors, then we see the decay is almost parallel to V2, the faster eigen direction. And when we are closer to the origin, the decay is more in the direction of V1, because V2 is already very small. Okay. Okay, on a side note, it is possible that here you will get lambdas that are irrational numbers. Okay, they might contain square root expression, and then you should carry this to this type of calculation. Okay, so here instead of some rational number, you will have an irrational number multiplying this, and you need to carry this until you find v2. Also, it might contain square roots. Okay, and so we carry the square roots until the end, and only then do we do an approximation just in order to be able to draw these vectors. I'm not going to do such an example because I don't have much time.
But it happens, doesn't happen in this kind of case, only in final node, right?
No, I'm not talking about complex numbers. I'm talking about something under the square root that is, say, square root of 31. Okay? Okay, from here, after we saw the properties of linear systems, I'm going to move on to the nonlinear systems. And not surprisingly, the way to deal with nonlinear systems is to linearize them wherever we can. And you'll see what I mean. Okay, so we are talking about a general form. X dot is some function of x and y. Y dot is some function of x and y, where f and g could be any type of function, especially nonlinear. And the advantage that this gives us over the linear system is that it allows us to describe more complex dependencies of the time derivative on x and y. For example, there might be a cooperation between x and y, right? Only when their product is large enough is the time derivative large enough, okay? There might be some normalization, okay? So x squared divided by y, okay? Always normalized by the present y coordinate. Okay, so you'll see when we discuss models, like population models, how this is important for us. Now, this type of system can, of course, have fixed points, okay? In the fixed points, we have both functions equaling 0. And of course, this can happen in multiple places on the phase plane. There might be many fixed points, not one fixed point like we saw in the linear system. Or over there were these pathological cases of a line of fixed points or a whole plane of fixed points. But here there might be specific points, a finite set of points in the phase plane. So for any such a fixed point, x star, y star, we can do a linearization, or we can try to do a linearization of the system. And here we are assuming that if we are close enough to the fixed point, to the specific fixed point that we are dealing with, then the higher order terms of these functions are negligible. And the leading terms are the linear terms, linear in x and y. So say we are at this fixed point, okay, x star, y star, our linearization assumes that if we are here, then any very small perturbation results in a linear behavior similar to what we saw in the linear system. And so we say that close enough to the fixed point, we know what happens here. Okay, we know how to solve the linear system that exists here, or is an approximation of the nonlinear system that is valid for this close vicinity. So this perturbation or disturbance we will define using new variables like the eta we had before. Okay, so u is the perturbation on the x-axis and v on the y-axis. And we are trying to see what will happen to u dot and v dot. Okay? After we made this perturbation, then how will it change? So what we do is a Taylor's expansion. Now, u dot is just equal to x dot, right? Because x star is a constant. X dot is just f of x and y. And what we are going to do is we are going to write this as f of x star plus u and of y star plus v. And we already did Taylor's expansion for two variables. Over there, it was the variable x and the parameter r. Here we have these two variables, x and y, or u and v. So our first term is the function evaluated at the fixed point. Our second term, okay, formally these have these terms in front of them. Our second term is this. Sorry. Okay, so first I'll explain what I'm doing. In the Taylor's expansion, we always have x minus x star, right? But instead of x, I am going to write x star plus u. Okay, according to my definition of the perturbation. What? I'm doing the expansion for f of x and y around x star and y star. So, yeah, you can say that x minus x star is u. So what I have here is u times the first derivative according to x at the fixed points. As a shorthand, I will just write a star here. And in the first order term, I also have the equivalent for the other dimension. Now my second order term okay, remember this is supposed to be x minus x star squared. So I'm just writing u squared. And then I have v squared. And then I have the mixed term, uv and higher order terms. So what I do from here is, of course, I eliminate, first of all, the zeroth order term by definition of the fixed point.
Could you just explain that why you do that?
What?
Can you explain why you eliminate that point again?
Well, f of x star and y star is 0 because we are.
Okay. Right. Yes.
Okay, so I'm left with u df over dx plus terms of order u square, v square, or u times v, which is also second order, plus higher order terms. And when u and v are small disturbances, when this is a very small perturbation from the fixed point, then u square and v square and u times v is extremely small. Okay. I'm saying that I can always make my disturbance small enough that these are negligible compared to these, unless these are exactly 0, of course. This and this, or yeah, okay. Unless these two are exactly 0. Yes.
If only one of them is 0, you still can neglect the other? Or
Well, no. If say this is 0, then my leading term in u in the x dimension will be the u square, but my leading term in y will be a linear term. Yes.
not general function, they are differentiable function.
Say again? Differentiable. Yeah. Yeah. True. Yes, but notice that I can do this for any point where they are differentiable. So if they have specific points where they are not, then I can't treat those, but I can treat the rest of the plane. Okay, and basically I do the same for the v dot. Okay, so this is the result. Of course, looks very similar. V dot equals u times dg this time, dg over dx plus v times dg over dy plus terms of u square, v square, uv plus higher order terms. And this is, if these are indeed negligible, okay, then, okay, if they are indeed negligible, then this is a linear system in u and v, okay? U to the first power and v to the first power. And these, remember, these are numbers because this is evaluated at the fixed point. You substitute the fixed point into this expression. So this is a number and this is a number. These are also numbers. And you have a linear equation on u and v. And this is the linearization of the system. So what we did here is equivalent to moving our coordinate system over here. So this is our new origin, and then we say that near the and then we say that we have a fixed point at the origin, as we had with the linear systems, and near the origin, the system is linear. If I write this in matrix form, so this is the same as what we saw in the linear system. And now you see the matrix that we called A in the linear system, and which controlled the properties of the system, whether the fixed point is stable or unstable, and so on, is now this matrix, the matrix of the derivatives. And this is what we have to analyze. And some of you probably know that this matrix has a special name. It's called the Jacobian of the system. So in our linearization, we find that the properties of the system around the fixed point depend on the properties of the Jacobian evaluated at the fixed point. So and then what we will do is we will look at the trace and the determinant of the Jacobian, trace and determinant, and then see where this falls on this plot, and whether we have a spiral or a regular node or a saddle, and so on. So the analogy of in the one-dimensional system would be the f prime x that we used to check whether it was a negative or positive or zero. So this was the derivative with respect to x. Now we have two dimensions, and we are looking at all these derivatives and at the trace and determinant of the matrix that is built from them. Okay. I'm going to carry this analogy further. In order to introduce the properties that we get in the linear system, in the linearized 2D systems, and how they determine the stability. So
just to clarify,
yeah,
so the purpose of all this is for classification of the fixed points?
yeah.
Okay, so we're not...
Well, not only. The first thing you want to do is to classify it.
So up until now, that's what this will accomplish.
Yeah, but from here on, you just treat this like a linear system, and you find the eigenvalues and the eigenvectors. Okay, and you'll see how by treating the different fixed points in the system, you start to build the phase plane, the phase portrait of the system. Okay, so remember what we had in the one-dimensional systems, where this was our sole equation. Okay, we looked at f prime x, and then it could be positive, and then we said this is an unstable fixed point. It could be negative, and then that was a stable fixed point. And if it was 0, we said that it needs further analysis, but can be seen from the geometric method. And then geometric method. And it could be also half stable, which is a special case. Now, you already know how the trace and determinant dictate the properties of a linear system. So what we are going to do here, I'm going to show this plot that is also applicable to the linear systems. Here, instead of looking at f prime and saying whether it is positive or negative, we are looking at the real component of each eigenvector. So when both eigenvectors have a negative real component, then of course this is stable, right? And it can be a node or a spiral depending on what is the imaginary component. Okay? And remember that the trace is the sum of eigenvectors and the determinant is the product of eigenvectors. Eigenvalues, sorry. Eigenvalues. So this is a negative trace and a positive determinant, of course. Here, when they are both positive, then the trace is positive, the determinant is positive, and we have an unstable fixed point, either a spiral, a regular node, a degenerate node, or a star. Now, when one eigenvalue is positive and the other is negative, we have a saddle. And of course, in this case, the determinant is negative. And we don't know about the trace, but we don't care. Also here, when one of these eigenvalues, or it's when one of these eigenvalues is 0, then this is the case of determinant that is equal to 0. When the trace is not 0, then we have a line attractor, right, or a line repeller. Okay, and when both of these is 0, then the trace is 0. We are on this axis. Okay, so we could have a center or either a whole plane of fixed points. And that is for the case where the determinant is also 0. Reaching the result that you have a whole plane of fixed points actually means that at this fixed point, um, this system is kind of very stable. You move a little from this fixed point, and you may be pulled back or pushed outwards very, very slowly. Okay, and probably these quadratic terms should come into play. I mean, if you got the determinant as 0 and the trace is 0, probably the linearization is not enough here. And the reason I did this table here is in order to show you that where in the one-dimensional system we moved from unstable to something that needs further investigation to from unstable to 0 to stable, we only had one axis. Here we see this behavior on the diagonal. Okay? We need to see the combination of both eigenvalues. So if they are both negative, we have a stable fixed point. If they are both positive, we have an unstable fixed point. And if they are both 0, then I would say that you should do a deeper analysis of the system. Okay, because you got a center or you got a whole plane of fixed points, and the linear terms don't matter. Okay, the linear terms will not pull you back into the fixed point from a perturbation. They won't push you away. But probably then the quadratic terms will be important. So this axis here is similar to what we had in the one-dimensional system. And since we have two eigenvalues, we have these mixed cases where we have this line attractor or line repeller. And when the eigenvalues are opposite in sign, you have the saddle. And now you see why there is no analog for the saddle in the one-dimensional system. Okay, just it cannot happen there.
Is half stable like a saddle, or it's not?
Say again?
Half stable is not like a saddle?
Well, no. No, because in a saddle, you are drawn on one dimension and you are thrown away on the other. And a half-stable fixed point is one that you approach from one side, and if you're on the other side, it's along the same dimension. Okay, you approach it from one side and you are thrown on the other side. Okay. You can have something similar to a saddle in the two-dimensional systems. Okay. We'll see these things as we'll see these later on as very special cases of fixed points. Okay, let's take a break. We'll take 10 minutes, and 10 minutes from now. Okay.
Can I?
אז א', נראה לי שאני כאילו מפסיד פה, איך כאילו מציירים באמת את הקווים האלה? כאילו, לירון הזה, כאילו מציירים על הוקטורים הנובעים. אז כאן שאתה רוצה לקחת נקודה רחוקה, ואתה אומר מי משפיע יותר, כלומר מי שניים אמור להשפיע יותר, אבל למה אתה חושב ב-V1 משפיע יותר? כי... הרי נכון הערך שהוא יותר קטן, אבל גם הערך על V, כלומר הערך על שניהם יותר קטן.
כן, אבל
V1
תחשוב, זה כמו שכשאתה... כשהערך שלך הוא קטן מ-1, אתה לוקח אותו בריבוע, אתה שונה, אז אתה מקטין אותו עוד יותר. אוקיי, בגלל ש...
אז מה
משהו יותר גדול אני יותר מקצין כאילו?
כן, כשאתה מסתכל על שני אקספוננטים, אוקיי, נגיד שיש לך e ב-x ו-e ב-10x.
לא צריך.
אז אני מסתכל על x של x, שניהם עוברים פה. שניהם עוברים פה, כן, פה עם ב-x. ושניהם עוברים פה. אוקיי, את ה-e ב-x זה קל לצייר, כן.
זה מעניין אותך שזה...
ה-e ב-10x הוא גדל יותר מהר, אבל פה הוא... בגלל זה, כשאתה בעצם... כשאתה בערכים קטנים,
כאילו, משהו שהוא יותר גדול.
כי עכשיו נראה שהאנלוגיה זה כאילו...
אוקיי, בסדר, אבל נראה לי שאתה יותר קרוב, אז בעצם V1 איכשהו... אז הדרך לצייר את זה בסופו של דבר, זה פשוט כאילו ללכת עם הכיוון של הוקטור, ואז כמו שאני... כאילו, ואני לא יכול לדעת סתם אם הוא מגיע ככה או ככה, או כאילו... כמו שהוא חוצה את ציר ה-X, וזה אני לא יכול לדעת.
לא, אתה לא... עכשיו אנחנו רואים את הדברים האלה, אבל בעיקרון... אתה יודע
פה נגיד, אני לא יודע איך הוא...
אתה צריך לחשוב שמערכת הצלמים החדשה היא המערכת של האייגנווקטור.
אוקיי.
ואז יש רק דעיכה על הכיוון של האייגנווקטור הזה. זה לא יכול ללכת לשם, הוא לא יכול לגדול.
לא, זה אני מכיר, הנקודה פה, איך היא מגיעה לכאן?
זה מין עקומה כזאת.
למה? אבל כאן הולך לפי הכיוון הזה, לפי הכיוון הזה, כאילו, ככה כאילו? אבל אז הוא הולך בדרך של V1, V1 יותר קטן.
כן, אבל אם תחשוב על זה תמיד הקומפוננטה של V הזה היא יותר גדולה.
כאילו, הקומפוננטה שלו אמורה לקחת אותו לכאן, אז הוא היה כאילו צריך לכאן. טוב, אני אתן לכם יותר גדול. אני כבר הבנתי את זה שזה כאילו הוא מקביל פה, ואז לאט לאט הוא מתקשר לו. סתם נקודות שהן מאוד קרובות ל-V1, אני לא בדיוק מבין מה קורה שם.
הרעיון הוא אתה נמצא בנקודה שרכיב ה-V1 שלה. אוקיי, נגיד זה V1.
הרכיב זה כאילו היתר על V1?
כן.
אוקיי.
נגיד ש-V1 הוא ה-IT, כן?
כן, כן.
אז כשאתה נמצא על נקודה שרכיב V2 שלה גם היא 1, אז...
פחות מושפעת ממנו בעצם.
כן.
למרות שהיחסים שלה יותר גדול.
כן, אז אתה יכול להגיד שאמרנו ש-V1 הוא ה-IT, נכון?
כן. אז
V1 הוא הכחול, כן? V1 הוא הכחול. נגיד שאתה נמצא בנקודה שבו רכיב V1 הוא 2. אתה יכול לדמיין שבמינוס זה שקול, כן? אז ב-2 אתה מקבל x דוט, כן? או v דוט שהוא כזה, אבל רכיב v1 הוא כבר קטן, כן? הוא נמצא פה והוא יותר קטן. זה בעצם מה שחשוב לך.
ועוד משהו חשוב, Alex, explain why these eigenvalues provide... מה זה
להסביר, לקשר בין הערך או הסימן של ה-Eigenvalues להתנהגות.
כן, נגיד, בכיוון הזה הוא דרך, בכיוון הזה הוא זה, ולכן זה נגיד סתם כדי לספר את הקצר כאילו.
לא, אבל יותר מזה, להגיד, ה-Eigenvalue הוא שלילי ולכן מצליחה ולכן...
אוקיי, סבבה. לגבי, היה פה את העניין הזה של התנאי התחלתי. אז אם בעצם הוא נמצא ממש על הישר, אני לא יודע, אין לו איזה שמות לזה? זה כאילו ה-direction של V2?
אפשר לקרוא את ה-Eigendirection, כן.
Eigendirection, סבבה, אז אני פשוט זורם אם אני, כאילו, זה קצת מפתיע אותי, כי אם הייתי פה, הייתי כאילו לא הייתי מגיע לנקודה.
נכון.
בגלל שאני נמצא על הישר, אני כן אגיע
נכון, כן.
לא?
לא.
אוקיי.
זה מה שנקרא stable manifold. manifold זה תת מרחב. אז במרחב דו
הנקודה.
אז בגלל שהתחלתי, כן, יש קו אחד, אם אתה מתחיל עליו במדויק, אז אתה נכנס לקו.
זה בגלל שהקומפוננט של V1 הוא 0 א'?
בדיוק, כן. אז אין מה שיגדל.
בסדר, אוקיי. בסדר גמור.
אתה יכול לדמיין שאתה יורד מכיפה לעוקף, כן? ואם אתה הולך בדיוק על הקו המולכת, אז אתה לא תיפול. ואם אתה תצא קצת, אז אתה תתגלגל למטה.
אוקיי, ועוד משהו רק לגבי הספירלה. בספירלה אני מסתכל כאילו בסך הכל כאל ספירלה אחת, או כאילו
כן,
יש המון, אני כאילו נותן את זה רק עבור מי שנמצא לספירלה.
בדיוק, אתה ספירלה אחת, כן. וזה מאוד מקורב כאילו.
סבבה. וגם לגבי הדירקשן. פה קצת, כאילו, שוב, מה שעשיתי אינטואיטיבית, לקחתי נגיד אחד והצבתי ובדקתי כאילו לאן הולך אבל, ואז כאילו המסבירה הייתה שאם C חיובי, אז הוא נגד כיוון השעון ונגד שלילי. עכשיו, כדי להוכיח את זה קצת יותר מסובך נראה לי, כאילו, מה שהתחלתי להראות זה שכאילו C ו-B חייבים להיות עם כיוונים מנוגדים, זה יצא לי איזשהו גם משוואה. אז אם הם לכיוון מנוגדים, זה באמת נכון, אם C הוא חיובי, אז בעצם, אז ה-Y הולך לכיוון חיובי וה-X הולך לכיוון שלילי, אבל זה בהנחה ש-A ו-B הם 0. אבל ברגע ש-A ו-B הם לא 0, אז לא, אז כאילו...
אוקיי, אתה לא צריך להוכיח, אתה לא צריך לקבל איזשהו חלק.
אוקיי, כי אם A ו-B הם לא 0, אז אני לא מצליח להראות שבאמת C הוא קובע אוטומטית את הכיוון. כי זה גם תלוי ביחס בין C ל-D. אם A ו-D הם 0, אני חושב ש-C באמת יקבע לאיזה כיוון הוא ילך. כאילו, כי אז ה-Y יהיה חיובי וה-X יהיה שלילי, ואז זה ילך נגד כיוון שלו. אבל ש-A ו-B הם לא 0, פה הסתבכתי. כאילו, לא הצלחתי להראות שזה...
כן, אני יכול לבדוק את זה.
אבל אתה אומר רק לתת איזשהו כיוון.
כן, רק לקשר רק לפי הדוגמה שאתה עשית.
לא משהו יותר כללי. טוב, מעולה, תודה רבה. זה כל כך.
Okay. uh, I already told you that if you land here on this table, if your linearization gives you an eigenvalue that has a real value of 0, then you might start to doubt the validity of the linearization and look at the higher order term. And in this course, we don't go beyond the first order. But what we do employ is evaluating the validity of the linearization. Okay, so we do the linearization and then we say in retrospect whether it was valid or not and whether we can trust what we got. Okay. So so can we trust the linearization? If we find a node, a spiral, or a saddle, then we would trust the linearization and we would say that this is the quality, that indeed we have the qualitative behavior of the system. The finer points arise when we predict a star or a degenerate node. Okay? Here we would trust the stability but not the qualitative behavior. So basically here, maybe in order to be more thorough, when I say qualitative behavior here, I mean also the stability. So when my linearization tells me that this is a node or spiral or a saddle, then I would say, okay, then I'm sure that I did get the correct stability and also the correct behavior, qualitative behavior. And here I mean, for example, in a node, this will be a growth or a decay that is linear along that goes along the two eigendirections, and in the spiral, uh, in a spiral, this will be an oscillation into or out of 6 points. And these are two different behaviors, and this is another thing completely. And this this makes sense when you think of our delta to tau plane. Okay, what I'm saying here is that if I predicted a node or a spiral, okay, I might be here or here. Then if my linearization is not very uh, is not very good, okay, if there are quadratic terms and so on that may be important even very near the fixed points, then that might change the trace or determinant of this behavior, okay? But to a small extent. So a node would still be a node, a spiral would still be a spiral, and so on for a saddle, okay? But if my linearization tells me that the fixed point is exactly a star or a degenerate node, then I may think that small quadratic terms that I did not take into account may be responsible for a shift that will dictate a spiral or a node. Okay? So in that case, I would not expect the small quadratic terms change the stability to move me from here to here. Okay? But they might take me off this line. So I would say this is stable, but I'm not sure this is exactly a star. So this is exactly a spiral. Or I would say, okay, I found that it's a star, but very, very close to the fixed point, it will become a spiral. Something like that. Okay?
Why can't you be close to the border between stable and unstable? Isn't that also just like a...
I might be, yeah.
So, but you said that we can trust.
Yeah, I don't expect. Okay, these are very special cases. So
Mm-hmm.
if my trace has a very minute value, but we don't look at that. Yeah.
Here we're talking only about the points that are very close to the fixed point.
Yeah.
Because we don't know nothing basically. It's not like the geometric method that we know about.
Yeah.
Just
In the linearization
just
around the fixed point. Yeah. This is only valid for the vicinity of the fixed point.
let's say you say that it's a spiral.
Yeah.
Just spiral in the vicinity. It's not.
Yeah. So what I'm saying is, if I found that it's a star, okay, star looks like this. I'm saying that the small quadratic terms, if I go a little bit out of the fixed point, they might show me that this is in fact a spiral. Okay. So I predict this, but I don't know what happens outside. And if I found a star, then I'm very doubtful of what happens outside. I won't be able to say for
Only
sure.
in the case number 2 and case number 1 you can know.
Yeah, in case number 1, I will be more confident in extending the behavior of the fixed point outwards. Okay?
But it's not for sure.
What?
It's not for sure. You're more confident.
No, it's never for sure. And probably even when I extend it outwards, there will be some range beyond which it will stop behaving like this node. Okay. So what I mean is that if I predicted a node, okay, then the behavior might look like this, like we had before, right? And first of all, I'm confident that this is stable. I'm confident that this is a node and not a spiral, for example. So I don't expect spiral behavior, okay, close to the node. Here, when I found a star, I do expect this. I expect either a spiral behavior or a behavior that starts looking like a node. Okay, so here, very close to the fixed point, it may look like a star, but a bit farther away, it might start twisting. I don't know how, but okay. But this is for drawing, and you'll see later that we have other tools for extending our trajectories beyond the fixed point. But this is for actually saying whether the linearization is valid. Yes.
What about other kinds of, like the line
The line.
attractor?
Okay, so just a moment. I'll finish saying something about this, and then I will deal with them. So all these are called hyperbolic fixed points. And their property is that they are robust. Meaning that the stability is not affected by higher order terms. Meaning the nonlinear terms. Okay? So this is a category of fixed points. And the hyperbolic fixed points are broadly classified into attractors and repellers and saddles. Okay? if I refer to the table I had before, so I had attractor, repeller, and saddle. Yes.
In the line attractor and line repeller isn't there should be also hyperbolic because
So they are not hyperbolic. So this is my next category. If we have some real lambda as 0, so this would mean centers and lines. Here the stability is highly sensitive to nonlinear terms. Okay, so you could imagine that I did the linearization and I found for a certain fixed point, right, that I get a line attractor or a line repeller, but this is a point, right? So I can say that in the vicinity of the fixed point, the linearization tells me that there should be some line attractor. Okay? In the vicinity of the fixed point, there is, say, only decay along one direction, and along the other direction, I find by the linearization that there is nothing, no movement. And then we say that it's very possible that the small nonlinear terms are responsible for a very, very slow decay into the fixed point. Okay, in which case it will be a node, or a stable node, or maybe a very, very slow running away from the fixed point, and then it's actually a saddle. Although I did not find it in my linearization, and this means that my linearization landed me here, but the small nonlinear terms are responsible, are actually make the behavior like this or like this. Okay.
but just to clarify this, so for you, line attractor and stable fixed point are two different
things. Yes.
Stability.
Yeah.
In terms of stability.
Yeah.
Okay.
Okay, so for the case of the center, you could imagine that, okay, you got by linearization that this is the center, meaning that if you are here, you stay here, but if you move a little away from the center, you revolve around it. If you move a little more outwards, you still revolve in a cycle. But then it's possible that small nonlinear terms will make this oscillation actually grow very, very slowly, or either descend very, very slowly into the fixed point. So in these cases, we say that we do not trust the type. Okay, we don't trust that it's the line attractor. We don't trust that it's the center, and we don't even trust the stability, because in these cases, very small nonlinear terms that are positive or negative are critical for the stability. Okay, so what I'm going to do now, after we saw the linearization and we saw the evaluation of the linearization, is I'm going to do an example. Okay, not on this. And through this example, we'll see what we do with the linearized fixed points and what we do with the regions in between the fixed points. Okay, now when we get nonlinear system like this, first thing we should do is check whether we can easily find 6 points. Okay? It might be that we cannot find 6 points analytically. It might be that we can find 6 points, but it will be very complicated, like requiring us to solve a cubic equation or so on, and then we won't even go into it. But it's worthwhile checking whether it's simple enough. Okay, this is a parabola, right? um, and y dot equals 0 gives me y equals x to the third. So I have these two equations, and the 6 points must satisfy both of them. Okay. Um, a cubic equation. I won't try to solve it, but in this case, I can guess a solution, and for the sake of the example, uh, I'll proceed from here. Okay. This is a solution, right? 1 equals 1 half plus 1 half, and then 1 equals 1 to the third. It satisfies my conditions, and the two functions are indeed 0 in this coordinate. Okay, now when we cannot do this, now we don't see the original equation.
You can probably erase that like work.
Yeah, but I'm trying to save it for later.
Yeah.
Okay, let's copy them. When we cannot find the 6 points analytically, or it's hard, then we have a graphical method to do this. And for this, we consider these curves that we found that satisfy x dot equals 0 and y dot equals 0. Okay, so remember, x dot equals 0 should occur on this curve. And let's plot this curve on the phase plane. This curve passes at 1, 1. Okay. When x is 0, the curve has a value of 1 half. Okay. And it's basically a parabola shifted upwards by 1 half and opened. Okay. It's less steep than just x squared. So this is our curve. Now on this curve, what happens is there is no x derivative. All the trajectories on this curve will go vertically. Okay, I don't know their direction, but I know that they go either straight up or straight down. I know that x dot equals 0 on this curve. This type of curve is called a melt line. Okay, because one of the derivative is null on it. Okay. And this is specifically the x naught, the x naught line. So I already have these handles for the trajectories that exist in the system. Now, the other null line, no, before we move on,
I didn't quite understand what what did you do here?
uh, I demanded x dot equals 0, and I got back this curve. So on this curve, x dot equals 0.
Okay, so what does it give you?
That if there is any change in the system, it's only along the y direction. Okay? And now, so the trajectories go either up or down. Above and below this curve, there should be some x component to the change with time. Okay? And I should be able to tell what it is. Okay? If y is larger than this expression, then x dot is negative. Okay? So I will draw this component. Anywhere above the curve, the x component at least goes to the left. And when y is smaller than this expression, then x dot is positive. So everywhere below this curve, the x component at least is going to the right. Okay? And you can imagine that if a trajectory makes a turn from left to right, it will be only on this curve. Okay? So trajectories may be coming from here and then making their turn here and then going back. Okay? Or if there is some oscillation, then you already can see how it's going. Okay? Yes.
Could you please explain again the change in the on the x-axis,
Yeah.
the evolution?
I'm looking at this equation in order to say what is the x component. This is my curve, y equals this. If I am at a point on the phase plane where y is larger than this expression, okay? So you see how it's okay, now let's look at the other null line. Y dot equals 0 gave us the expression y equals x to the third. Pity I don't have a red pen. You have one? Oh.
Something here.
Okay. Yeah. Okay. I'll see what I do with it. There are other things as well that I want to draw. Okay. So this is approximately y equals x to the third. And using the same considerations as before, on this curve, everything should go either right or left. There is no y component along this curve. There is only an x component, okay? Because y equals x to the third, and this is 0.
But how did you know how to draw this?
What? How do they know what?
This the new curve.
Y equals x to the third.
Ah, okay.
Okay, so now
No, I mean the green lines.
these,
Mhm.
they must be horizontal. This is all I know right now, that they are horizontal, because on this line, y equals x to the third, and y dot equals 0. There is no change on the y direction. There is only change on the x direction. So the system, if it is on the curve, it will go either left or right, I don't know,
Okay.
but it will go...
But this goes, the other curve is going just not left and right. It goes like up and down.
This one, yeah.
Yes.
Yeah, on this curve you go only up or down. On this curve you go only left or right.
How come?
Because
Why?
they are the curves that give you x dot equals 0
Okay.
or y dot equals 0. So here I do know the direction because I already plotted it. Everything below the x naught line is going to the right. Everything above it is going to the left. Okay? Let's add labels. These are the labels for the naught line. Now, what I want to determine is what happens with these directions. Okay? So, if y is larger than x to the third, then this is positive. So anything above this curve, this area here is above the curve, has a positive y component, and specifically these vertical directions, they should go up. And everything below the curve, and specifically these directions that I already marked, they should go down. Okay? Now, these were just auxiliary. I don't want them to confuse you right now. So I have my naught lines, and I have the directions of flow on the naught line. Okay, now I'm going to treat the areas between the naught lines. Okay, I have several regions here delineated by the naught line. So this region is below the x naught line and it's above the y naught line. It should have this general direction. This is very general. Okay, but it helps me see where the system is flowing. Okay? It is going up because it is above the y naught line, okay? To the left of it. This is why it's going up. It's going to the right because it's under the x naught line, like we found for these. So it agrees with the arrows most close to it. Okay, this region here should have a component going left and a component going up, okay? So it's basically going this way. This region here should agree both with this and this arrow, so it's going here. And this region agrees with the arrows close to it, with the arrows on its border, in fact. So the flow is this diagonal. Now this is very general. Remember that our trajectories cannot make turns unless on the naught line. Okay? So here nothing can go to the left because in order to go to the left you must make a turn, right? You must pass on this line. So everything here is going to the right. And also everything here cannot go to the left. And same for the up and down direction.
And for the one on the x-axis,
Say again?
beneath the graph, um, between 0 and 1.
Here?
Yes.
So this is the same region. Also here you have a direction that goes over there.
And under the...
And here this is the same region. Unless you pass an outline, you have the same direction. Only if you pass an outline, you go from down to up, okay, or you go from right to left.
Okay, so under the curve,
Yeah.
before the 1.
Here. Here.
No,
Here.
yes.
It's the same. see if you find it as we go along. Um, okay, so now what happens with the fixed point? We can already make some assumption about it based on the flows that we see. But remember, it was not trivial to find the fixed point from this. Okay? However, when we plotted these two curves, one of them having x dot equals 0 and the other having y dot equals 0, we did get the fixed point. It's the intersection of the node line. Okay? So we didn't have to guess. We could go on and plot the node lines and see if they intersect. Okay, so this is a fixed point at 1, 1.
But you don't know where the fixed point is.
Excuse me?
Only looking at this, you don't know where it is, what the value is.
Well, you know that both curves pass at 1, 1. I mean, you use that in order to draw them. Okay? And at least you can get a vicinity, some range where you suspect the fixed point is, and then you can, maybe it will help you to find the exact value. Okay? In your exercise, excuse me?
You can further expand around that approximate point, and then even if it's something which is very difficult, you can use some linear approximation and find the linear approximation of the point.
Yeah, you can do that. You can do Newton's method in order to find it numerically. But whatever you find numerically and not analytically, you cannot put into the Jacobian matrix and get the tracing term. Okay? Because it would be invalid. It will not be the exact fixed point. Okay? In your exercise, I think you have an example where you cannot actually find the fixed point analytically, but you can tell whether, for example, it's smaller than 1 or larger than 1/2, and you can see from the Jacobian matrix that when you put this range of values in it, you should get some specific trace or determinant, positive or negative or so on. So even if you cannot find the fixed point analytically, you can maybe see geometrically where it should be, and it already gives you clues, and you can infer at least something about the Jacobian. Okay? Yeah.
Can we be sure from this graph that the fixed point is a saddle, or it can be also something else?
Yeah, that would be a good guess. Okay, a reasonable guess.
But it can be something else.
Probably not something else, no.
How can it be something else?
Yeah, I don't see how it can be something else. It could be that the linearization will give you a line attractor, but then you'll say, I don't trust that, and by the arrows here, I see that it is a saddle.
And why is it a saddle?
You see, here things go into the fixed point, and here things go out. You don't have a behavior of everything going into the fixed point or out of it. You have some arrows going in and some arrows going out.
But how did you know to draw the right lines downwards and the left lines upwards?
Because
And not the other way around.
because I looked at this equation. Okay, up or down is y dot, and I'm asking where is y dot positive and where is it negative. So when y is larger than x to the third, that means above the curve, this curve of x to the third. Okay.
Right.
When y is larger than x to the third, then y dot is positive. So above this curve, everything goes up. And below it, everything goes down. Okay? Okay, so we have a fixed point. We found it geometrically, or we guessed. And now we are going to do the analysis for this fixed point. So the first thing we do is write the Jacobian. Okay, you tell me what is the first term in the Jacobian, df to dx. Remember, this is f of x.
It's a 1.
No, it should be x.
Yeah, but they fix it before 2, so.
Yeah, don't substitute just yet.
Okay.
We don't substitute yet. Okay, so what is df to dy?
One.
Minus 1. What is dg to dx?
Minus 2.
Yeah, and dg to dy?
1.
Just 1. Okay. So usually I would find the Jacobian as a general expression and then use it because I may have several fixed points. Then I will substitute several fixed points into this. Okay, so the Jacobian at the fixed point 1, 1 is 1 minus 1 minus 3, 1. The trace is 2. Determinant minus 2. Okay, negative determinant already established. Yeah, and you can do the plot of trace of determinant versus trace and locate it on that. So I mark a saddle by an open circle. It's generally unstable. It's not attracting. It's not yet more stable. Okay. We are going to do now the eigenvalues and the eigenvectors of the Jacobian, and they will help us draw the trajectories of the system. But before we do that, I will say that I did not manage to teach the Lotka-Volterra model today, and it is the third question of your exercise. So there will be an extension on the exercise, either to the Thursday after next class or to the Monday after that. Okay. So I can cover that material, and you can do question 3. Okay, so I'm looking for the eigenvalues So this is, yeah. Okay, so lambda 1 is 1 plus square root of 3, and it's positive. Lambda 2 is 1 minus square root of 3, and this is negative. Okay, a saddle point has eigenvalues of opposite signs. Now, I'm going to look for the eigenvectors, okay? So for lambda 1, I have so if I write the first equation, I get S1 minus R1 equals S1 times 1 plus square root of 3. Right? These cancel out. So R1 equals minus square root of 3 S1, and V1 is 1 and minus square root of 3. When I do this for the second eigenvector, it's very similar. get v2 equals 1 square root of 3. Okay, so let me draw for a moment the close vicinity of the 6 points, because they don't have much room over there. Okay, this is u and v, remember. I'm drawing these two vectors that I got. 1 minus square root of 3. Square root of 3 is something like 1.7. Does anyone remember? I don't remember. Okay, so 1 minus square root of 3 is something like this. This is v1. And v2 is 1 plus square root of 3. At this point, I would write an approximation. 1 minus 1.7. Only after I have reached a final answer that is exact, I can write lambda 1 is about 2.7, lambda 2 is about minus 0.7. So along v1, this is lambda 1, I have growth, right? Along v2, I have decay. And in between, I have this pattern of a saddle node. So now, I would like to complete my phase portrait and draw some trajectories. Okay, so I start by doing this. I try to draw the vectors that I found. Okay, maybe in red, in black. Okay, and I'll do in red the trajectory. So okay, so these are the eigendirections, and the pattern of the saddle, these trajectories going towards the saddle and then outwards, they must make any turn from right to left or from up to down on the null line. Okay? So for example, a trajectory coming from here should be vertical on the null line and then join this direction. Okay? A trajectory coming from here should be horizontal on the null line and then go over there. And the same goes for trajectories here. They are horizontal on the null line. And these trajectories should be vertical on the null line. Okay? Now, the behavior of the saddle is valid for the vicinity of the saddle. So these eigenvectors may not hold, okay? They don't go on for infinity, okay? Farther away, we might have nonlinear terms coming into play. So I don't know what happens here. Right now I will draw this straight, but it doesn't have to be. Okay, for example, here, probably this cannot go on forever. Okay, it must conform to the null line. It cannot cross the null line and remain in the same direction. It might do this. I don't know. Yeah, probably goes like this. And now I can start filling in the plane anywhere horizontal, it should be horizontal on the y-naught line. And if it's anywhere vertical, it should be vertical on the x-naught line. And here, you're allowed to speculate, okay? But you must comply with these conditions, with these requirements. Okay, so for example, I could have lines going like this, right? And then lines going like this. Lines coming from there. There is a certain line that is going into the saddle, but anything else is doing this. Okay.
Only one line going in and out the saddle?
Yes, only one line. This is the stable manifold, like we learned. Okay, and so on and so on. Okay.
You need to draw the whole plane or only the
Say again.
You need to draw the whole
Yeah.
or only the
Well, it's nice to draw the whole thing.
nice. That's why.
What do you mean by nice?
I like it. I like to read it. It kind of gives you a feeling that you know what's happening in the system. Yeah, I encourage you to try and draw the whole thing. Okay. Okay. Now I wanted to show you this on the computer, but we don't have time. I have the simulation with the null lines, and then you can pick a small point, and then it will show you where the system goes from there, and it's very nice. Maybe I'll do it early in the next lesson, first thing in the next lesson. Okay, so that's it. Now you know how to analyze a nonlinear system and infer what happens in the fixed point, outside the fixed point. And next lesson we'll see the Lotka-Volterra model, and then your exercise. It's a model for populations.
But what did you say at the beginning?
Lotka-Volterra model. And then your exercise view this as performed. I'll post a message with the date.
And עכשיו מדברים על דומים יותר
כן.
נגיד אני מתחילה, אז הבנתי את אלו. עכשיו גם את הדפים השחורים גם הבנתי. אוקיי, אז כזה, כאן אבל שכאן, זה חופר את ככה. אבל איך, מה הדומים?
הדומים מחברים את המסלול אדום. אדום זה מסלול
הקו הזה, נכון?
התחלנו באיזשהו
הקו, אז יש לי כאילו
למה
זה הקו הזה?
זה יכולה כאילו ממש ארוך.
כאילו היה חוצה,
בכל מקום שהיא נמצאת, היא יכולה לציין את הכיוון הכללי.
אתה יודע שהוא חייב
אם היא עוברת למטה,
אז חייב בחשוב זה כמה נגיד שלא
לא, אבל זה אתה לא יודע.
לא, אבל אתה יודע שלא יכול לחצות אותם כי תמיד צריך להגיע להם אז אם
אתה יודע
לא, נגיד הוא מישהו לידו, נגיד כן זה לא הייתה את זה מישהו לידו כן יוצא והוא דווקא הגיע להם אבל יש לדעה שזה סאונד או אתה יודע שיש איזשהו קו שתמיד מגיע וכל השאר כאילו לא מגיע אני מניח שיש עוד מקרים אבל אני לא חושב שאתה לא, זה דבר קו, כאילו הקו הזה שבטוח מגיע לעצמו אתה לא יכול לדעת שלך
כן, אתה לא יכול לדעת, אבל נגיד אתה יודע שהוא באזור הזה ואתה יודע שהוא לא
לא, אומר מה אני מוזרזת
למה אנחנו בעצם עושים את זה, כאילו את השלב הזה? למה אנחנו לא יכולים ישר?
זה בגלל שאין שם הרבה מקום, אז רציתי
לא, אומר, מה אתה עושה ליניאריזציה? היית יכול לפי החלקים האלה לנחש איך
נכון, כן
אבל אז מה נותן לך הסביבה הזאת? אתה יודע שזה סאדו
לא, אתה יכול לדעת מהחלקים שזה סאדו
סאדו אתה יכול, אבל נגיד
טוב, אבל זה נראה לי, את הקו הזה לא הייתי יודע שזה
כן,
למה? הייתי יודע
היא נותנת לך את אלה של מין עוגנים תראה, אתה בהחלט יכול לצייר ציור די גל בלי לעשות את הליניאריזציה זה באמת, זה מה שתעשה אם לא תוכל למצוא אנליטית את הנקודה. אבל אנחנו כל הזמן מנסים לדחות מהמשוואות כמה שיותר מידע, כן, בלי להיכנס לחישובים לפתרון של משוואות דיפרנציאליות מסובכות ובלי לעשות סימולציה נומרית.
כן. כאילו את אומרת שזה
זה ממש הכי הרבה מידע, כן, אז פה, כן.
אפילו נוער פה, שאומר בחינאים, ושם נעליים סגורות, הבינה שיקר מדי.
אוקיי, וגם אם זו הייתה נקודת שבט יציבה, אז זה היה עוזר לי לדעת, אתה יודע, את הפנימיות של המסלולים.
האמת שהדירה שלי
שיכול להיות שהייתי גם מבין אותו מהנאופלינות, אבל זה עוד משהו שאני יודע בוודאות. שוב, בוודאות לסביבה הקרובה. אתה צודק. אבל הגישה היא תמיד לנסות עוד קצת ועוד קצת
כן, אבל כאילו, אז למה בעיקרון, אם אנחנו ניקח את הליניאריזציה ונחשב גם את ה... כאילו בסטיילר, בטור טיילר נחשב גם את החלקים שהם יותר, שהם אור של ריבוע. אז זה ייתן לנו יותר מידע? אנחנו לא עושים את זה סתם מתוך כאילו...
זה ייתן לנו יותר מידע. כן, זה יכול. כן, במקרים הגבוליים. במקרים הלא גבוליים, זה חבל.
תנסה בחוזה שלך לתקן
מה קרה לו שלא?
כן, אבל אני לא מכירה מישהו
מה קרה?
התקרה שלי, היא נזלה כמו, ואז היא יורקת עליך ריחות של טבע. זה התקרה.
אבל יש...
נורא נחמד, אתה מתעורר, ואז כמו שלג, אבל זה לא באמת טבע.
מה הבעיה לך איתו?
הוא אומר שהוא יחזור עליי. לא, הוא ממש, אני מה שתפתי ממש מנסים לדבר איתו, והוא קשה.
כן?
לא כמו מופיד, בפנינות שלו, פשוט לא תמיד הפעם.
למי יש לנו?
תזמיני מישהו שיתקן ושמישהו
לא, תלוי מה יש לכם בחוזה.
לא, אבל אין לי זמן לזה, התקשרתי למישהו, ואז הוא אמר לי תדריך עוד יומיים. אני התקשרתי לבעל המקצוע ואין לי יומיים.
כן, כי אחרי הסערה כולם מתעסקים נורא.
זה ממש בעצם.
למה עכשיו שהתפוצץ לה?
אוקיי, אם... small plane effect point אתה מקבל כשהטרייס הוא 0, זה הדטרמיננט A0.
אוקיי, שזה לא בראשית,
כן,
כאילו.
רק בראשית.
כן.
בסנטר אתה מקבל...
זה הקו הזה שהוא מעל, אוקיי. אוקיי, ואיך יכול להיות ששניהם 0 והטרייס לא יהיה 0? כאילו בשניהם לא יהיה 0, הטרייס לא דטרמיננטה?
רגע, עוד פעם?
אם גם הריל, החלק הריל של...
כי יש imaginary.